In this video, we're going to start section 6, which is found in chapter 6 of our textbook on chemical reactivity and mechanisms. Specifically today, we're going to look at energy diagrams in 6.1. An energy diagram is a curve which represents the change in energy of the system as the reaction proceeds. And the progress of the reaction is referred to as the reaction coordinate. Now there's two aspects that we normally will focus on when looking at an energy diagram. We're going to consider the kinetics of the reaction, that is the rate of the reaction, how quickly or how slowly a reaction proceeds from reactant to product. As well, we're going to consider the thermodynamics of the reaction. So we're going to be looking at the equilibrium that exists between the reactants and products. In some instances, the equilibrium is non-existent. It's unlikely. In other instances, there is an equal proportion of reactants and products at any one point in time. And so the energetics associated with that is given as the change in the free energy of the system as we go from reactants to products. Whereas when we're looking at the kinetics of a reaction, we're really focusing on the amount of energy, which we refer to as the activation energy, the amount of energy required for those reactants to overcome some barrier to product formation. So again, the kinetics refers to the rate of a reaction, while thermodynamics refers to the equilibrium concentrations of reactants and products. Now, a reaction with a low energy of activation often will occur faster than a reaction with a higher activation energy. And so as you can see in these two energy diagrams, when we plot the free energy of a particular reaction against the reaction coordinate, the progress of the reaction, if we compare left and right, we see that there's a substantial difference in the height of this barrier. And this height corresponds to what's called the activation energy. And so the smaller the barrier, the faster the rate. Less energy is required for the reactants to proceed through this transition state towards products. Whereas if the barrier is substantial, quite high, that's going to have a major effect on the rate of the reaction. The reaction will be slower as a result. And so it's often, I think, helpful to think of these reactions as these are millions of molecules, moles of molecules interacting with each other, colliding with each other, lots of collisions. But there's only a certain fraction of those collisions that actually lead to reaction. And it has something to do, or a large part of the success of a reaction has to do with the kinetic energy associated with those reactants. And so if there's a small barrier to product formation, more of those collisions are going to be successful. So a larger fraction of collisions will be successful. Whereas if there's a higher barrier associated with the activation energy, a larger activation energy, then a smaller fraction of those collisions and the kinetic energy associated with the molecules, a smaller fraction will be successful. When we think about equilibrium or the thermodynamics of a system, however, we don't concern ourselves so much with the rate of the reaction, but how the energy or free energy of the products compares to that of the initial reactants. So any process with what we call a negative delta G, these reactions are generally spontaneous, and this process is called exergonic, and that's shown in the left energy diagram. The energy diagram on the left is that you see that the free energy of the products is lower than the free energy of the reactants. So if we take the free energy of the products and subtract the free energy of the reactants, we'll end up with a negative delta G. And so this is an exergonic process, and these reactions are spontaneous. meaning that we don't require additional or significant amount of energy for this reaction to proceed. Whereas if the process has a positive delta G, that is, the free energy of the products is higher than the free energy of the reactants, we refer to this as an endergonic process. So in this energy diagram, we're showing two possible pathways that a reaction between A and B can take. We can end up with products C and D, or products E and F. And so if we were to predict which products would form, we would most likely choose C and D for two reasons. One, the activation energy is lower for the blue path. So there's less energy, kinetic energy required for A and B to overcome this particular energy barrier. So that's going to increase the rate of the reaction. It's going to be more competitive with the red path. So the path of least resistance, in a sense, is the blue path as opposed to the red path. Secondly, from a thermodynamic standpoint, the free energy is lower for C and D, which means that that product, that set of products, is more stable. And so the difference in energy between C and D and A and B, the overall free energy difference, will be more negative as a result. The more negative the delta G value, the more spontaneous the reaction will be. Now, if we look at this particular example, we have a scenario where thermodynamics will favor one pathway, but kinetics will favor an alternate pathway. So you can see that in this case, C and D is favored thermodynamically, with the more stable products will be C and D, but via the red path, it will be kinetically favored. And so we will sometimes encounter reactions in chemistry where you have one set of products that are favored kinetically, but another set of products that are favored thermodynamically. And normally, given time, all products will result in the more stable set, meaning thermodynamics will give rise to your final product set. But initially, you may find that an alternate product set, in this case E and F, may form initially, and then through a reverse process back to A and B, and then forward, you may encounter the formation of more of C and D. So we have thermodynamic products and we have kinetic products, but given time, our net result will be the formation of our thermodynamic products. But initially, you can have, over a shorter period of time, kinetic products may be favored. So that's how we look at the energy diagrams and how we use them to explain the kinetics and thermodynamics of various organic reactions. Now, reactions often involve multiple steps. Unlike what we saw in the previous example where we had just a single maximum, in an energy diagram of a multi-step process, we'll also have what we refer to as local minima. And these local minima, as highlighted in this orange areas, these are referred to as intermediates. These are short-lived species, but we can detect them spectroscopically, and in some instances, we can isolate them. Whereas local maxima, these peaks represent transition states. So what's shown here in green are the transition states between the various minima along the path. And so transition states, on the other hand, these are fleeting. These are not as easy to detect spectroscopically, but we'll talk about that on the next slide. So a transition state, this is a state through which the reaction passes. And as we saw, that can be simply from reactant to product, as shown in this energy diagram, or in the last figure, that could be between two intermediates, a reactant and intermediate, or an intermediate and a product state. So these transition states, these are not easy to isolate, meaning we can't collect the species at the transition state and put it in a bottle. These are very difficult to monitor and assess. And really, up until recent time, they were theoretical constructs. They were our best guess as to what bonds were forming and breaking at that maximum. Nowadays, with the technology advancements with respect to light sources, similar to what's found in Saskatoon at the CLS, but now we have these larger facilities known as XFELs, these free electron laser systems. Europe has them, Japan, US. These types of systems produce such bright light and such short time scales that we're getting better at really elucidating the structure of transition states such that we can actually say that we're detecting them and spectroscopically following them in real time. So it won't be long, it'll be in our lifetimes, your lifetime for sure, that we will be able to really map out these reactions with 100% clarity. And we're going to be able to make what we call as molecular movies of how reactions occur. So it's an exciting time to be in science. So you can see in this example, this is an example of a substitution reaction where we have this methyl bromide. And at the end of the day, the product state, we're going to substitute this bromine atom for a chlorine atom. So you can see that the final product is this methyl chloride or chloromethane. So you can see that at the transition state, we have the carbon-bromine bond of bromomethane starting to break, whereas the carbon-chlorine bond is starting to form. So again, this high energy transition state is really the process where these bonds are being formed and broken as the reactants proceed to products. Now, an intermediate, on the other hand, this is a species with a relatively short lifetime, but one which we can still detect spectroscopically. So with commercially available equipment today, we're able to detect the presence of intermediates and determine a lot about their structure in those short time scales. So they may only have lifetimes of 10 to the minus 9 a nanosecond or 10 to the minus 12 a picosecond, but nonetheless, with common day spectroscopy, we can detect them. And in some instances, we can isolate them, but generally speaking, we observe them spectroscopically. They're very difficult to isolate and store. So in this example, we have a tertiary butyl group attached to a bromine atom. This is known as tertiary butyl bromide. And in this substitution reaction, we'll still end up with the bromine being replaced by a chlorine atom, but it doesn't happen in a single step. You can see that we have 2 steps in the process, and the number of steps in the process can be counted by the number of transition states in your particular energy diagram. So you can see from this energy diagram, we have 2 barriers, one and then a second one to get to the final product state. So we have a transition state associated with the transformation of the original reactant to this intermediate, as you can see, a carbocation, as well as the carbocation undergoes a transition as it reacts with the chloride to give you the final product. And so here we have a transition which results in the dissociation of this tertiary butyl bromide to give you the carbocation. So we've broken this carbon-bromine bond, and that results in the formation of a carbocation and the bromide. And then in a second step, we have the chloride reacting with the carbocation to give us our final product. And again, these reactions can be reversible if the barrier of the intermediate back to the reactant is not too high. And so there's going to be thermodynamics playing a role in that there will be an equilibrium associated with this initial generation of carbocation. But as you can see, when we form our product, the free energy of this new tertiary butyl chloride is significantly lower than the initial tertiary butyl bromide. And so thermodynamically speaking, this is a very spontaneous reaction, and these products are quite stable. So if you have any questions about energy diagrams and the information that we can gather from them, please send me an email. We can set up a Zoom appointment or start a discussion in our forum. Thank you.